Oh, shit, sorry.
All right. So, the latest lecture notes are available, and I won't be here tomorrow. My daughter's getting married.
Oh,
Good. Anyway, so if I'm more insane than usual, that's why. But Andrew Forbes, very talented young man, will be doing the talk session.
Bloch sphere, Bloch sphere, Bloch sphere.
Yeah.
Do we have homework to, do you know if that's graded or?
I believe it has been, and PTAs will be emailing it back. Yep. All right, very good. So I just quickly, just one quick piece of review. So again, just to emphasize some of the analogies and things what we've been saying. So we spent, a whole lot of time talking about longer precession of a spin in a magnetic field driving, and it's because it's really an important problem when we want to think about the way in which we manipulate quantum coherence. It all comes down to that. And in particular, the problem we're interested in at the moment is the two-level atom, okay? And as we said, well, as one of my advisors said, there are no two-level atoms, and sodium is not one of them. That was there's a reason he said that, but I'll come back to that maybe some point. Nonetheless, we can think about a good approximation to that, where we think about driving between two levels of an atom, typically between the ground state and some excited state, although it need not be. We can think about two high-line states that are metastable and driving between them. But typically, we're thinking about this problem. And we're driving it with some laser or electromagnetic wave that has, we're for the moment thinking about it as monochromatic. It has a single frequency. It has some amplitude and phase at the position of the atom. R here is the position of the atom. And we're potentially not on resonance, so there's some laser frequency. Or I'll just call it the light frequency. It doesn't have to be optical. We could think about this with microwaves.
Amazing.
We could. And so when we are sufficiently far off resonance from all other levels, or they're not connected because of selection rules, we restricted our attention to this two-dimensional subspace, in which case my Hamiltonian is the bare Hamiltonian of the atom, where we just restrict ourselves to these two energy levels. So the Hamiltonian is diagonal in the basis of its energy eigenstates with eigenvalues here. And the interaction Hamiltonian is the interaction of the electromagnetic field with the charge distribution that's associated with the atom. But that, to lowest order approximation, the strongest interaction when the wavelength is large compared to the size of the atom, remembering the story of the multipole expansions, that the dominant effect is the electric dipole interaction, okay? So that's typically a good approximation, unless it's not. And the times in which it would not be a good interaction is if this matrix element, which is not quite correct, were zero, because if the matrix element were zero, we'd say that that would be a transition which is dipole free, okay? Well, this, even if we have neutral, that the question of whether you have a monopole interaction is a different story. Excuse me. This is just saying something about whether or not this matrix element is non-zero or not. Yeah,
For omega EG, should it be the difference of energy over H bar?
you should. So, assuming a dipole allowed transition, we have this problem where the role of the Larmor precession rate is now, that is given by the energy scale associated with the dipole interaction. Okay, so the Rabi frequency is related to the dipole matrix element, and the strength of the electric field depends on the intensity of the laser. That tells me something about the amplitude of the electric field. And when we restricted this Hamiltonian to the two-level subspace, it has the same form as the transverse, oops, this is not quite right, because that's in the rotating frame. So this is the form of the interaction that we have when I make the rotating wave approximation and I dropped the counter-rotating terms, okay? So I've already made the rotating wave approximation when I've dropped the terms that had to do with GE with an e to the plus, and vice versa. When I make the rotating wave approximation, this is the interaction Hamiltonian, okay? So we've mapped the two-level atom onto spin resonance. But again, this has nothing to do with the spin of the electron. This is not a magnetic interaction, unless it is, unless we're actually talking about states that are coupled by not an electric dipole matrix element, but a magnetic dipole matrix element. Then that would be actually related to the spins, right? Okay, so what we were talking about the last lecture was the so-called optical Bloch equations. And in particular, so the time evolution of the quantum state of the two-level atom can be expressed in terms of the Bloch vector. So the Bloch vector is a way of representing the state of the system, right? Where the U component is the mean value of sigma x, and sigma x is sigma plus, which I'll write like this, and sigma minus, which I'll write like that, which is rho GE plus rho EG, which is twice the real part of that. So the U component of the Bloch vector is related to the coherences. It's related to the off-diagonal matrix element, V, is the expected value of sigma y. Sigma y is sigma plus minus sigma minus over I, which is rho G E minus rho EG over I, which is 2 times I, the imaginary part. Okay? So that's to say that the off-diagonal matrix element, rho EG, is U plus IV over 2.
When you
you say imaginary part, that usually means that it's a real part of the imaginary. So you have
No,
to-
no, 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 the imaginary part is a real number. So if I write a complex number as x plus iy, this is the real part, this is the
Yes,
imaginary
exactly,
part.
exactly. So what do you put in either?
Oh, because I was you're totally right,
Yeah.
because I'm totally wrong, yeah. But that's what I mean, excuse me, yes, thank you. Okay, so, again, these are the components of the Bloch vector, which is a way of thinking about the state of a two-level system, okay? So, but now we're not thinking about it as the direction of a physical spin, we're thinking about it as a direction of an abstract Bloch vector, which is just a way of representing the state of this two-level system. Moreover, W, which is the Z component, is the population difference. It's the probability to be in the excited state minus the probability to be in the ground state. Yes, Sam?
You have a rho GE there, and then over there you have rho EG. Should that be rho EG as well? Or?
This should be, sorry, you are absolutely right. Both of these, the signs correct, it's GE. That is correct. Thank you. Okay. So from this, we had equations of motion, the Schrodinger equation in the rotating frame is Larmor precession of the Bloch vector, okay? So what we have is, you know, the Schrodinger equation, which we could write in lots of different ways. We could write it as the equation for the state vector, or we can write it as an equation for the density matrix. All of this in the rotating frame. And if we take the expectation of sigma x, sigma y, sigma z, we get the Bloch vector Larmor precession. Okay? This is just the Schrodinger equation, but written in a very crazy way in terms of the Bloch vector, but it is just the Schrodinger equation. And that gives us then equations of motion for these guys, right? And that tells me that the u dt is equal to, and I won't get the signs right, so I better get my notes out. This is the one thing I can never remember. Sorry about that. Let's go back to this and let's, oh good. All right. So these are the equations that Bloch wrote down as the Bloch equations. They're just Larmor precession around omega effective, okay? Where I've taken the phase of the laser to be 0 in this case. Otherwise, I'd have more components of this. All right, so what we talked about at the end of the lecture, we're going to continue now, is, well, I mean, we know that Larmor precession doesn't persist forever. It will decay and it will relax, okay? And so we can put in phenomenological decay. And say that there is exponential decay with a time scale we call T2 for the components that are related to the coherences. And in the absence of any driving, this says that u and v will exponentially decay to 0. And they will exponentially decay to 0 at a rate that is 1 over t2. Okay? So this is my decay term. And in steady state, these guys decay to 0, whereas in steady state, the population inversion doesn't necessarily decay to 0. In fact, if this was a 2-level atom, where this was the ground state, what would you expect the steady state to be in this case? The ground state. And the ground state corresponds, if everything is the ground state, then W would decay to become -1, right, in steady state. So that means that we should write the equation such that the decay term here is -1 over some time constant that's called T1 minus whatever the equilibrium is, in this case, +1. So that in steady state, this derivative is 0, W would go to -1. Okay, is everyone clear? That's why, whereas these things decay to 0. So that's our phenomenological decay. And that gives us terms of the optical Bloch. Yes, Tristan?
So we don't, and these phenomenological decays, we don't need to know where they come from. We are claiming they exist.
For now.
We see.
We'll come back to talk about this in a moment, like at least some, where would we expect to see this? But it's really in the same way if we think about an oscillator, a classical oscillator, we know that that oscillator will not persist forever. The energy will decay, and those decaying oscillations are due to friction. Now, we could, if we wanted to, microscopically model friction with, van der Waals forces coming on, and with, an entropy and things going somewhere. But we could just lump it, if there's friction, and we know this is effectively a friction force. Yes?
When dWdt takes that form of the decay, am I assuming essentially the system is isolated, like an isolated Riemann system?
Yeah, so this kind of evolution is what we call, as you might say, isolated closed. This is a closed quantum system. And we have unitary evolution. But when we have decay, well, the evolution is no longer described by the Schrodinger equation as written. We'd have to think about that more carefully. So, right. So, again, if we put back this all together in terms of the definitions of U, V, and W, in terms of the elements of the density matrix, as we've written there, we can write the optical Bloch equations in terms of an equation of motion for the different components of the density matrix. Let me just write that down over here. So, the optical Bloch equations would say that this guy, if I put this together as we did last time, minus the detuning, minus 1 over T2, rho dt, minus I over 2 omega, rho gt minus rho e, which is equal to the complex conjugate of the other guy, and rho EE, right, that's, remember this is the time derivative of U plus IV over 2. This is the time derivative of 1 plus W over 2. Putting that all together, I get the following equation, minus 1 So this equation is an equation of motion that has this the Hamiltonian evolution plus something having to do with dissipation. Okay. We've put these terms in by hand. We did not derive anything. We just said there's going to be some decay, and phenomenologically, this is what we expect. Okay? This equation, though, has a name, and we're going to derive it from first principles next semester. It's called the master equation, because it's sort of the master of all statistical mechanics. And this is related to the fact that this is an open quantum system, that there are other degrees of freedom beyond the two-level atom and the classical field that we're not accounting for. In the same way as friction, there are all the other degrees of freedom that are associated with the touching of the surface and how heat or entropy gets in the surface interactions that makes energy not conserved. Where is it going? Well, it's going into the other degrees of freedom. Okay? Notice, though, what we said, if we had a closed quantum system, the entropy was conserved and the purity was preserved, right? So if we were particularly on resonance and we started our Bloch vector like this, we know that what will happen is we'll just get Larmor precession, and the magnitude of Q is 1 for all times if we have a closed system. This is just the Larmor precession that we had. But what does the Bloch vector do in this case? It is no longer going to stay on the surface of the Bloch sphere. It will have some other trajectory. This trajectory is one in which we have complete reversibility, and this would go on forever. But in practice, that doesn't happen. What happens is the system ends up somewhere with some steady state. It will have some steady state value of U, some steady state value of V, and some steady state value of W. And we're going to study those steady states in a moment. I'll get to your question in a moment. But the thing few things I want to emphasize about this picture is that when we have this, purity decreases. Entropy increases. In the same way as I talked about for friction, right?
Oh my gosh.
And so we have the situation where the Bloch sphere, the Bloch vector is no longer on the surface of the Bloch sphere. The trajectory of Q goes interior to the Bloch ball and has some kind of finite entropy and purity decreases. Yes?
So, based on this, in looking at the equations of motions on diagonal and off diagonal terms, it seems to me if my purity is changing or my coherence is changing, that's going to affect the way that my population.
That's right.
Thought physically, right?
So it is. What you're seeing here is important. The coherences drive the population change, and the population inversion drives coherences. That's the way this works. That's how the evolution happens. Again, I want to emphasize when in this picture, to the degree to which the T1 and T2 times are negligible, when we turn on this laser, and let's say we started all the population to a good degree in the ground state, at a later time, it's not just in the excited state. There's some chances in the excited state, there's some chances in the ground state, but it's in a coherent superposition of the two. And in fact, if we turned on this thing on resonance such that the Rabi frequency times the time were pi/2, we would do a pi/2 pulse, and we would create an equal superposition of those two. Now, of course, we would have to do that very fast compared to the T1 and T2 times, because otherwise it's not going to stay there. It's going to end up here. Tristan, did I miss your question? I'm sorry if I
You got
did.
it.
Okay. Yeah.
Why are there only 2 T terms? Why not 3?
There could be, but typically, it just phenomenologically, the decay that, and we'll come to this in a moment, where are these things coming from, really don't depend on the U versus V. The coherence itself is what decays. The real and imaginary parts decay in the same way.
I see.
Yeah, but let's maybe talk about that, right? So what is going on when we have T1 and T2 times? Let's look at these equations again, okay? So remember, generally my density operator, I can always think about it as some ensemble decomposition of pure states. Okay, so that's just, I have some ensemble decomposition of pure states. So my, say rho EE component would be equal to this. If I think about each of these guys as some superposition of the ground state and the excited state for the particular ith term, then this is what this is, and rho GE is that, right? That's the off-diagonal term. Or I can write this like so the T1 terms, the same thing for rho GG, the T1 decay is related to the decay of population. When I say population, that's a old-fashioned term that we use representing the fraction, if I thought about the probability as the fraction of those atoms in a large ensemble that were in them, we call it a population. But really, it's the probability, okay? But we use those terms interchangeably, okay? And so, the T1 times will be related to that, but what about the T2 times? Well, there can be, the T2 times are going to be related to the decay of population as well, right? So if there is a rate of decay, so I might say if I had a decay rate of the excited state, then T1 would be equal to 1 over the decay rate of that. Okay, if let's say the ground state were stable, but the excited state, okay, then T1 would be 1 over the rate of decay of the excited state. coherences? Well, there's going to be, in this case, so this is related to the decay of population. So that is to say, the amplitude decays let's say the amplitude as a function of time decays with a half of that, so that the square decays with this. Okay? Is everyone clear with that? They would say that the population, which is the square of the amplitude, decays with that exponent. So we typically call the T1 time the rate of, well, not typically, we always call it the rate of decay of the population, which is the rate of decay of the square of the amplitude, which means that the amplitude squares with half that rate. Okay? So if I look at the decay of these guys, if I had no other driving, how would this decay? Well, generally, let's imagine an ensemble where every one of these amplitudes decayed at the same rate. Okay? So I could take it outside this. That would be equal to CEG at 0, e to the minus gamma t over 2. And maybe the ground state, let's be more generous. Let's say the ground state is metastable and also decays. So what did I do here? I said every one of these guys is decaying at the same rate. It has some amplitude, and that amplitude is decaying. It's decaying at a gamma such that the population decays, and so gamma over 2. So this would tell me I have rho g e at time t equals 0. I'll write it like this. So, what we see from this expression is one conclusion. Even if I don't worry about this stuff, I'll come back to this stuff in a minute, the coherences are going to decay if the populations decay. So at a minimum, the rate of decay of the coherences, which is 1 over T2, is equal to that, okay? At least that. So if populations decay, coherences will decay for this reason. However, there can be additional reasons why the coherences decay and decay much faster. Typically, the T2 times are much shorter than the T1 times. The rate of decay of coherences are typically much shorter than the decays of populations. Why? The answer is here. Because if each of the members of the ensemble get some kind of random phase shift, then that is going to give me a random unknown phase in the superposition. And if I average over all those random phases, I wash out the coherence. For example, let's go back to this picture. Let's say that these atomic levels are sensitive to stray magnetic fields. There are stray magnetic fields everywhere. There's currents flowing around with 60 hertz of current, and there are, current makes magnetic fields. and they're there. And so these guys, what's that gonna do? It's gonna give me a little energy level shift of this guy and a little energy level shift of that guy that's related to that. Which will mean that there will be a phase accumulated in the amplitude. What phase is accumulated in a small time delta t given this? So, well, it's not, there's nothing resonant here. It's just that the energy is shifting. And what I'm saying, because the energy is shifting, the relative phase in a superposition between those is shifting. What would be that phase?
The frequency of the laser?
There's no laser here. It's just that there's the energy, there's string magnetic fields.
The final
And-
initial distance of the energy levels?
Say again.
The final and initial levels of the energy?
That's right. So those different energy levels, so this phase difference between these two is what? By the Schrodinger equation. How much phase is accumulated on the amplitude?
That is 0 pi by 2.
Something to do with h bar?
Well, I'm saying this phase is related to these energies. The Schrodinger equation, how much phase does the amplitude get when I have a certain energy? Energy times time. It gives an e to the minus it. So if the energy shifts over some amount of time, I have a little delta E times some delta t over h bar. That's how much phase. So if there's a random flipping around and I have to average that, this is going to give me another kind of decay, depending on the probability distribution of those phases, right? So this probability distribution will matter. But typically, not typically, but often, I could get an extra, this whole sum, because of these random phases, gives me some additional decay. Which means that the T2 times are typically small compared to the T1 times because it's much easier to cause an energy shift than to cause the population to go from one state to another. So for example, let's say I just have atoms in a gas, and it's a vapor cell, it's got reasonably high pressure, and I'm driving it with this laser. Okay, so it's not a magnetooptic trap, it's an old-fashioned vapor cell, and it's got a lot more pressure, and the atoms are colliding. What's gonna happen? Well, when they collide with one another, I could get an inelastic collision, which causes the excited state to go to the ground state, or an inelastic collision or an elastic collision where I don't change the population, but the electron clouds overlap with one another. There's some energy accumulated. So typically, I'm going to dephase quickly due to those collisions, and my T2 times will be very short, okay? So in a qubit, in a quantum computer, it's typically T2 that is the problem. T1 ultimately, well, is a problem as well. Yeah?
Well, in that instance, if this sort of blurring of the spectral lines, when I lace my system, wouldn't I need to be considerate of my line width then?
Yeah, but I understand there's a lot of background knowledge, but we're building up things here. There's no lasing. There's nothing. I'm right now, at the moment, we'll come to this, hopefully, and get through this lecture. We'll talk about the laser rate equations at a moment. This is just saying I have a two-level system. My two-level system might be the ytterbium atom in, atom computing's quantum computer, where the ground state is the actual ground state, and excited state is the so-called triplet P state, and I have a UV laser. It's not UV. I don't know what it is. It's actually a nice optical frequency, and I'm driving Rabi oscillations between them. And the question is, do the Rabi oscillations do this? And to what degree do they do that? There's no lasing here. No lasing. It's totally coherent evolution. We'll come back to the whole question about the relation to the rate equations in a moment. That evolution is the Schrödinger equation. It is not the rate equations at all. And we're just asking, how does this thing decay? The bad professor. It's the wrong word. Okay. Did you have a question?
Yeah, when I think of decay, I usually think of the second law of thermodynamics. But this all comes from the Schrödinger equation.
No, it doesn't. So you're right, it does. The Schrödinger equation is this part.
I see, there's an additional...
There's an additional effect that we have not derived, we just put in by hand. And we put it in by hand, and we say, phenomenologically, we know that this is true. And I was just saying that there were going to be decay terms related to how the populations decay, and decay terms of how the coherences decay. The decay of the coherence has two components. If there is decay of populations, there will be decay of coherence. But there can be faster decay of coherence due to other physical effects. Yes, Tristan?
So would it be like fair to write, you have d rho by dt equals, and then the d rho by dt of the open system, like the way that it's leaving,
That's right.
plus the d rho by dt of the closed
That's right.
system.
That's right.
Is that like idea of the open plus closed system, like, does that make sense, or is that all just that
No, it
works?
does make sense, except the one added complication of that is that there's the interaction between the system and the environment. And the interface between them is buried in here.
Oh, okay.
Yeah. And so it's not like, here's the system, here's the environment, there's the system and the environment together.
So for now, thinking of this equation as a given fact is
Yeah, it's phenomenal in the same way that when you do freshman physics and you put friction on the sliding block, you don't say, well, where did that come from first? You just say, there's definitely some way this thing is not going to slide down the block 1/2 gt squared. It's going to have a drag force, and this is the drag force. It's a drag, but that's just the way it is.
So you added air resistance in the quantum mechanics? That's the best part of quantum mechanics.
Okay, so let's talk about at least one way that we know for sure there will be a T1 and T2 effect of my two-level atom. Okay, so here's our two-level atom again. It's up there, I'll draw it over here. And I'm driving it, at some ways they're near resonance, maybe. And, you know, there's going to be some amplitude here, some amplitude here, and it's going around. Okay? Why would this thing decay? Why wouldn't the oscillations go on together? What physically, for sure, is going to be there?
Spontaneous emission?
Spontaneous emission. The excited state of the atom has a finite lifetime. Okay? And why does it have a finite lifetime? I mean, I thought it was an energy eigenstate. I mean, if it's an energy eigenstate, then we also call that a stationary state. And if it's a stationary state, it means the probability to be there should be there forever. Yeah?
Because related to energy in the vacuum or something like that?
Right. It's because, it comes back to Tristan's question, is where are the hats on my electric field? You know? And the point is, really, there is a hat on the electric field. We just neglected it. We're going back to it. It's what most of the rest of the semester is going to be about once we, around fall break and beyond, is quantizing the field. But because of the coupling of the atom to the environment, which is always there, called the vacuum, the atom is not isolated. It is always coupled to the quantum noise in the quantum fluctuations of the electromagnetic field, it will spontaneously emit. Okay? And in the same way, you know, when you do the harmonic oscillator and you think about there's a natural resonance frequency and I say there's friction, I can think about that by putting an imaginary part in the frequency. In the same way, we can ask the question, can I say that the energy of the excited state now has an imaginary part, which I'm going to say is h bar omega, or h bar gamma over 2, where gamma is the spontaneous emission rate. Okay, so gamma is 1 over the natural lifetime. Why would this be a reasonable thing to do? Well, if this were the case, and I looked at my Hamiltonian now as of the atom, I'll call it the effective Hamiltonian, as having a ground state, which I'll say doesn't decay at all, an excited state, which has this imaginary term in it, then how would, if in the absence of any driving, how would the state evolve as a function of time? Well, let's say at time t equals 0, I was in the excited state. And if this were the Hamiltonian, what would the state be at a later time?
Yeah, the exponential decay on it.
e to the minus I of h.
Time evolution operator, everyone's favorite.
Yeah.
No.
Right? So in this, if this were the Hamiltonian, which is not Hermitian, but I'll come back to that in a moment, but this is a non-Hermitian Hamiltonian, then we would find that the probability to be in the excited state as a function of time is what? Well, it's the square of the amplitude, which is,
E negative gamma.
that's right. And that's in fact correct. If we were phenomenologically, if I were to do a pi pulse, and I did it extremely quickly, and then measured what's the chance of being excited state, I'd find exponential decay. Okay? Now, what's wrong with this? This is absolutely correct. But what's the probability to be in the ground state as a function of time in this problem? If this were the initial state, I use this Hamiltonian, what's the probability to be in the ground state as a function of time? 0. There's no refeeding. Okay? So this cannot describe the actual evolution because population is not conserved. In this system, because I have a non-Hermitian Hamiltonian, the norm of psi as a function of t is decaying. And that's not consistent with what we think about in quantum mechanics.
We gamma 1 minus E.
Well, no, and that's an excellent question. The answer is no. There's no way, there's no differential equation I can write down for a single state vector that would allow me to both have decay of population and preserve that. I need to go to the density matrix. And the reason to think about it is that this problem is random. There's a quantum jump that happens. There's no equation of motion. I cannot write down a Schrodinger equation for spontaneous emission with an effective Hamiltonian because of this randomness. Yeah,
But you can write the stochastic Schrodinger equation.
but that stochastic Schrodinger equation is not a determinant. I'm saying there's no
No.
we'll come back. You're absolutely right, Jay, and I'm kind of setting the stage for
Okay.
things
okay,
to
so
come. But in fact, as we will see, that stochastic Schrodinger equation, that random Schrodinger equation, does not describe spontaneous emission. It describes a different process by which we condition on seeing those photons, not on the open quantum system. But we're getting way ahead of ourselves. Okay. However, so if I come back to this, the master equation here, has the following form. I challenge you to take this operator equation and look at its matrix elements. I say that this equation is in fact this.
We believe you.
And what was that?
You said we believe you.
You can do it.
Yeah,
There's a bunch of matrices, you can do it. Where H effective here is equal to H minus I gamma over 2, the projection. This is a non-Hermitian Hamiltonian.
Yeah.
Okay? The part, what is this? Let's write this out. This is G, E, rho, E, G. Right? I just wrote out that term. Which is equal to what? It's equal to rho E, E times the projector on G. So what does this term do? This term refeeds population into the ground state. And it does it at a rate that depends on how much population in the excited state that decays back into the ground state. The refeeding term is the term I cannot get. This is the Schrodinger equation, but with a non-Hermitian Hamiltonian. But the refeeding term cannot be expressed in terms of a single Schrodinger equation. Yeah.
I thought you were going to like justify how this non-Hermitian Hamiltonian is just kind of works, but it's not, doesn't reflect reality. But then we're using
It actually does. It totally does. It just doesn't it doesn't capture everything. It captures the decay, but not the refeeding. The decay is completely described by an imaginary part and a non-Hermitian Hamiltonian.
So can we think about like an incomplete theory? Like it's like kind of describe some part but doesn't describe the whole.
It doesn't describe, it won't, it's incomplete, it will not describe this two-level system because, as we just described, the population won't be preserved.
Yeah.
But it does describe the decay out of the excited state. I'll come to your question in one moment. But here's something to think about. Suppose I have a three-level system, okay? I have some excited state, some ground state, and some metastable state. Okay? Such that every once in a while, the population can decay here, but it takes a very long time to decay here. And I want to just describe this problem. It's not trace preserving because I'm looking at a subspace. It is not correct to say all quantum evolution must be trace preserving. It's only trace preserving if you include every possible state in the Hilbert space. If you look at a subspace and only are interested in dynamics within the subspace, then I can have non-trace preserving. And then I can totally get away with writing my Schrodinger equation with an imaginary part to the excited states, and just because the refeeding terms are negligible in the context I care about.
So when you say right now, this is that if you only look at the subspace, you can get away with trace preserving.
You can have non-trace preserving.
But then all that other thing you talk about, like you only have two-level system and you ignore all the other states. Is it only because the other ones are way above, or is it just because?
No, it's because my laser was on resonance with this, but not that. So the two-level system was which systems were coupled in the dynamics. These two levels were coupled in the dynamics. This guy is so far off resonance, if I started here, nothing, the laser would not at all drive that. I'd have Rabi oscillations between these two guys.
Yes, but then if you put in the excited state, there's a probability of decay to
It's true. So that I can't, this won't cover everything, but I can have other systems. This was just, there's a lot of details. I can go into many places where I can have something which is effectively non-trace preserving, where I have a effective Hamiltonian with an imaginary part. That imaginary part describes decay, but not decay necessarily to the states I care about. We can talk more about that in detail afterwards. Okay. So, for spontaneous emission, T1 is 1 over. What about T2? If I have no other collisions, no Zeeman, I said that T2 will always be there because of decay of population. So what is the T2 time if I just have, yes?
1 over 2 gamma?
Close. It's 1 over gamma over 2, right? Where is it? Oh, it's here. So, T2 is 2 over here. So in this case, the T2 time is actually twice as long as the T1 time. Yeah. Yeah.
For those we have 2 gammas, right?
It came from the fact that I have 2 amplitudes.
Right.
And the amplitudes decay as gamma over 2. This was gamma because this was gamma over 2, but then I was looking at the population, so that was twice that.
That's right, there we have the gamma E, gamma G.
Yeah, over 2.
Okay, so the gamma E, gamma G are not equivalent to just gamma.
They are. If I had a 2-level atom, let's say this guy was 0 and this was gamma. Let's say that the excited state decays with the rate gamma, and the ground state doesn't decay at all.
Okay.
Then my 1 over T2 would be gamma over 2.
Okay. And how come the doesn't decay for the ground state?
That's right. So in the case of spontaneous emission, if there's no other collisions or no other dephasing terms, this guy would actually be bigger. Yeah?
The additional term you add to your equation of motion, is that also something phenomenological? Should I think that it's like a correction?
No, I mean, so, when we wrote down these phenomenological decay terms, because it was in terms of the in terms of the Bloch vector, and we write rho at any time as 1/2 the identity times q dotted into sigma. If we write the state in this way, what is the trace of rho as a function of time?
1.
1. By definition, the way we represented this, we ensured that population was preserved. It's just that coherences were lost and population went hither and whither, but we didn't lose any population. And thus, this equation has to be trace preserving, and the way it does it actually is this. So the phenomenological equations have this form. This is an example of what's known as the Lindblad master equation, which we will discuss in much more detail, but we didn't derive it from nothing. We just wrote it down by just saying, there's decay. And when we did that, we found it had this form. All right, I want to, in the next 10 to 15 minutes, talk about your question about the laser rate equations. Okay, so let's look at our master equation. Here it is. I'm glad I didn't erase it. And let's try to solve what the dynamics are in steady state. So I'm taking this laser, I shine it onto my atom near resonance, or maybe it's a quantum dot, or whatever it is, NV center in diamond, you know, for those of you who are working on that kind of stuff. It's all the same. And so let me get the lecture notes out here. Okay, so what do we, I shine a laser on my two-level atom. And I'm going to, what's going to happen? Well, I'm going to drive the system. It's going to Rabi oscillate. Firstly, I expect the population in the excited state as a function of time to no longer go on forever, but should undergo some kind of damping to some steady state. Right? So it's like a damped harmonic oscillator. What the steady state value will be the solution to these equations. In addition, the coherences will decay. It's decaying because of spontaneous emission. Photons are being scattered by this late. The atom is scattering photons because it's absorbing them and re-emitting them. We call that, in electromagnetic wave, the scattering of waves, right? Yeah.
So we were talking about a situation where one of the states, two-level atom,
Yeah.
ground state. Would there be any reason for us to or to not to pick the first and second excited states? Because that seems like it would change the math we're doing a little bit.
Well, yeah, if we did that, we'd have to worry about the decay of both of those states. We would change it somewhat. But let's think about this problem, okay? So let's relate this problem, I don't know, am I British? Where the heck?
French.
Let's think about this problem analogous to the classical problem of we shine on electromagnetic wave on an electron bound to the nucleus. We solve that classically by the way Lorentz did it, thinking about the binding as a harmonic oscillator and the Lorentz oscillator model, right? And so what's going to happen is if I think about this classically, I might think about an electron bound to the nucleus. And I shine on this light with some electric field, and I'm going to cause this electron to oscillate. I'm going to induce a dipole moment in this, and that induced oscillating dipole radiates. That's called the scattering of electromagnetic waves. Atoms do the same thing. I have my electron cloud on the nucleus, and I'm moving it relative to the nucleus, and that is what is causing this thing to radiate. Spontaneous emission is intimately related to just oscillating of the dipole. Okay? So let's first ask the question. So this is the Lorentz oscillator model. I put on some notes there to remind people of it. If you haven't studied it in your E&M, in my class, we sure do. But let's think about the following question. What is the induced dipole moment? Okay. So
Just call it
the induced dipole moment is when we think about it in steady state. The way we typically solve this problem classically is that we say, oh, there is a resonance frequency, there's the frequency of the drive, and there's some friction of this oscillator, and that's how we solve Lorentz oscillator matter. And we say, once the transients have died down, I have induced a dipole moment. Okay, so let me ask you the following question, just from classical mechanics. If I have a charge on a spring, and it has a natural resonance frequency, here it is. You're getting sleepy. Okay, you're already sleepy. Anyway, and now I drive it with some frequency that's not the same as this. After transients die down, at what frequency will this charge oscillate? The frequency of the drive, okay? So, you know, the induced dipole moment, if I have this thing, is going to have some component. So let's say that this electric field is, as a function of time, has some amplitude and it's oscillating like cosine omega t. Let's just take the phase to be 0. Then this thing will oscillate at frequency omega, which means anything that oscillates at frequency omega can be always written as some amount that arises cosine, some amount arises cosine. I could write this as the real part of the electric field e to the minus I omega t. So this thing is going to be equal to something e to the minus I omega t. I'll call this the complex amplitude of the dipole. The complex amplitude of the dipole has a real part and an imaginary part. The real part of this complex amplitude is this, and the imaginary part is that. So the solution to the motion of this electron will be that the electron will move such that some part of its oscillation is in phase with the laser and some part is in quadrature. Always. That's just mechanics and a single oscillator, okay? So in steady state, the induced dipole would be that. The same thing will be true quantumly. And let's find out what the induced dipole moment is. Okay, so let's do that. What is my induced dipole moment? Well, the induced dipole moment is the expected value of the dipole operator, okay, as a function of time. And I want to find this in steady state. Okay, so how would I do it? Well, how do I find this expectation value? Well, that's equal to the trace of the operator with the density operator. And we have the equation, but we have to be a little bit careful because we're working in the rotating frame picture. So we have to make sure that the operator is in the rotating frame, right? Because we made that transformation. So this is going to be equal to the trace of rho in the rotating frame with the d in the rotating frame. Okay. The equation of motion for this is that I didn't write RF everywhere there, but that's where we are. We're in the rotating frame. I'm just calling this rho just because I'm lazy and don't want to carry it. But how do we get the dipole in the rotating frame? Well, we have to make the unitary transformation. The dipole operator was the dipole matrix element times this plus this. Okay, that's the dipole operator, where this is the matrix element, which I took to be real, which I can, because I could just choose the phase of the wave function. That's in the lab frame. We have to go to the rotating frame. So when we go to the rotating frame, what do we get? Well, D in the rotating frame, I just rotated. I got very dizzy. Where U here was the rotation around the pseudo z-axis by an angle that depends on the drive frequency. We went into the frame co-rotating around the z-axis at the frequency of the drive. That's how we went to the rotating frame. Before it was omega naught, that was the longitudinal magnetic field. Now it's the laser. Okay? I mean omega of the drive. So this, when we do that, what we get is this guy, e to the plus I omega LT EG plus e to the minus I omega L GE. Okay? So, let's plug that in to this expression. What are we going to get? Well, we get that the mean value of the dipole moment as a function of time is equal to the dipole matrix element e to the I GE plus e to the minus I omega T EG. All those guys are in the rotating frame, right? Which is equal to this matrix element twice the real part of e to the I omega T rho GE. Right? Because this plus its complex conjugate is twice the real part of that complex number. But this was a half U plus IV. So this is equal to DEG U of T cos minus V of T sine. Okay. So, what do we see here? What we see is that the oscillating dipole depends on the coherences. The fact that the dipole is oscillating is because there is a superposition of ground and excited state, and that superposition is moving in such a way that the electron cloud is going up and down. That superposition tells me where the electron is, and it's moving up and down in some, and its mean value, and it oscillates in this way. In steady state, these guys will be some constant, and this thing will oscillate at the frequency of the drive. And the amplitude, how much dipole I have, will depend on these components, okay? Where the U component tells me how much I'm oscillating in phase, that gives rise to dispersion. The amount that I'm oscillating in quadrature is related to absorption. If you go back and you remember Lorentz oscillator. So finally, going back to this picture, if we look at this, this was my steady state, I don't know why I call it SC, it's SS for steady state. Here's my steady state dipole moment, Bloch vector in the rotating frame. What does it do in the lab frame? Well, in the lab frame, this guy is processing. It's processing at that frequency. So there is an induced dipole moment that is oscillating. The amplitude of that oscillation will depend on how close I am to resonance, how strong is the Rabi frequency, how much things decay. But I'm gonna get an induced dipole moment, and that induced dipole moment is radiating and will be scattering the light, okay? So this picture of a charge moving up and down is still true. It's just the trajectory is not the classical trajectory anymore, it's the quantum one. But it's not the whole story, because at some point in steady state, I could have the case where, let's say, the coherences are tiny and I have a completely mixed state. Then it's really quite different from the classical Lorentz oscillator. So, those notes are on for you to read. We'll pick this up next week and continue discussion and get to those laser rate equations and the connection to that as well.
Thank you, Professor.
All right.